In this video, we're actually going to start by skipping over example number 5. We're not going to cover this example in a video, but if you're interested in how I can actually derive the volume for the volume of a sphere, you can go ahead and take a look at the completed notes online up in Blackboard. And of course, I'd be more than happy to answer questions about that if you have them. But we're going to go ahead here and start to see how example 6 is going to play out, because we'll see that sometimes this idea of using cross sections that are circles doesn't work so nicely, but not in the way that it didn't work nicely in the previous video where we actually needed multiple integrals. But here we'll see something even more different begins to happen. So let's take a look here. I want to find the volume of the region that's enclosed by these curves once I rotate it around the x-axis. So I'm going to go ahead and sketch my region as I normally do. I'm actually only going to really need my first quadrant here. I have my quadratic function looking something like this, and then I have my line y equals x, which is going to look something like this, kind of moving through in this direction. And so the space that I have is actually just this little amount of space that's existing in here. Now, if I want to go ahead and rotate, as the problem suggests, around the x-axis, well, I can start in the same way that I normally do. I'll go ahead and I'll create a picture with enough space to create that mirror image of my region. Now, since I have two curves here, kind of like a top and a bottom, I'm going to go ahead and I'm going to start by drawing my top curve coming out of the origin like this, but I'm going to draw my bottom curve kind of lightly, or in this case, you'll see that I'm drawing it dashed. I would highly recommend that you try to do the same thing, and then when you draw your mirror image, you can also try to do the same sort of thing. So I'm going to get something kind of like this. Now, the reason that I draw the dashed line on the inside is just so that my picture doesn't get too cluttered up. Now let's take a look here at what's going to happen when I start to play connect the dots. Notice I'm going to start by picking an x-coordinate and going up and putting a dot. Now over here, notice that I'm going to really only have one dot because my functions have an intersection point here. And if I was to go ahead and draw this coming out of the page and then going back into the page, I see that same circular kind of shape that we normally see. However, watch what happens if I was to maybe pick another value of x, like over here, and try to start creating some points. Notice that there's going to be a point on the line and a duplicate point that I can go ahead and connect right away. However, there's also going to be a point that's going to exist on this dashed parabola that I'm going to need to connect and dash. And if I was to go ahead then and shade in the region that I'm left with, I will see that I get a region that looks something like this, and I'll notice this is not the shape of a circle. It's pretty close, but notice that it tells us a lot about how this solid actually looks. Imagine that I took this shape right here, which is kind of like a circle with a hole in it, and imagine I was to pull that shape further to the right. If I did that, you could imagine that the size of the hole would actually grow, because everything between these two parabola dashed shapes here is going to correspond to empty space. So as I pull this to the right, I'm going to get a bigger open empty space. And if I push it to the left, that empty space is going to shrink. So again, let's take a look at the online 3D grapher to get a better sense of what's going on here. If we switch over to this, what we can see right away is that we need to just adjust our top and bottom curve in order to create our region. We saw that our top curve was given by the line y equals x, and our bottom curve was given by y equals x squared, which is already written in here. Now, I can also see that I'm going from 0 over to 1, and that we indeed were revolving around the x-axis or the line y equals 0. So this right here actually does correspond exactly to the region that we're using. And so we can start to see again what happens when I take that individual rectangle, like one that might exist, say, right in here, and I begin to take that rectangle and rotate it around my x-axis. Notice again that as it comes out of the page and starts to move around, we can see that gap that's existing in there, right? That space between the region and the x-axis that was not shaded creates this hole. And again, depending on where that particular rectangle starts, like we had just said, that hole either becomes larger in the middle, or as I move down over here, this hole kind of slowly just disappears. Okay? So this is what we actually have in terms of a single individual cross section. It's not a circle. It's this new sort of a shape that we're going to have to figure out how to deal with. But again, when I kind of put all of those shapes together, I can see that I create this 3D solid that looks like this. Again, it's kind of almost like a bowl type shape. I have this divot that exists here in the middle that you can kind of see. Right? So I have something that's really nice and kind of a bowl-like here with just this kind of divot shape in the middle. So this is the solid that we're working with right now. We need to figure out how to get its volume, but again, that's going to be made more and more complicated, or at least slightly more complicated, by the fact that when we take a look at an individual cross-section being rotated, I create one of these washer shapes. So I have a big problem here. This shape is not a disk, and so I cannot use a disk method like we've done in the past several videos. But here's what I can conclude. I can see here that the cross sections stack horizontally. That is, they stack up left to right, and so we have a dx question. We can integrate with respect to x, but what we integrate is going to have to change. So I'll say here, since our cross section is not a circle, we cannot use the disk method. That will not work. But if I am able to find the area of a shape like this, then everything should actually still be perfectly fine. So if I can just try to figure out what that shape looks like and find its area, I'll be in business. Well, take a look at the next page and you'll see that I've kind of taken a shape like this and I've kind of sketched out over here this shape of this kind of ring that we actually have in the picture up above. We're actually going to refer to this shape very commonly as a washer. So if I have this shape, what I'd be interested in determining is what's the area of that band that we have. So I'll start here by saying first we will call this cross section a washer. Okay, that's what we'll refer to it as. And we want its area. So we want to find the area of this cross section. And to do that, it's actually pretty simple. Obviously, I can't do pi r squared because I don't have a circle, but I kind of have, well, I guess 2 circles. You can kind of imagine that I have this big circle here that has a radius that you see I've marked with capital R, but I also kind of have this smaller inner circle here that I've given a radius of little r. And so maybe I could go ahead and do the following. The area that I want could be found by saying, how about I take the area of the entire big circle, so all of this, that's the blue and the black space included, and then if I could just kind of erase out the area of that black space, I'd be golden. But the area of that black space is another area, but just of a smaller circle. So it would look something like this. Of course, I might notice that if I wanted to, there's a pi in common there, and so I could factor the pi out. But oftentimes, I'll just deal with this first instance here, because I like it better as thinking of one big circle minus another circle, almost kind of like I've punched out that middle area. Well, with this now in mind, it seems pretty easy to get the volume here. I would just have to figure out where my big radius, this big R is, and where that small r is in my picture. Now I'm going to go ahead here and try to zoom in on my picture to see if I can try to draw this. So let's see. My big radius would be occurring from this point here and going all the way up to this point. That would be my big R, my big radius. My small radius would be going from this point just all the way up to the edge of the empty space, and that's my little r. If I can figure out how long those are, then I am able to set up an integral here. So let's think about how we would actually do this. Let me just slide this back over. Okay, so if I was then to go ahead and try to set up the volume, I could see that my volume here is going to exist as, let's see, a pi big radius squared minus pi little radius squared dx, because I'm stacking horizontally, and my bounds will just state where these cross sections exist. Let's focus first on the radii, since we drew them. I can see my big R starts all the way up at the top here at my line, which was y equals x, and goes all the way back down to a y coordinate of 0. So that big radius appears to have length x minus 0. I can see that my small radius in green goes all the way up to that parabola function, which was my square y equals x squared, and goes down to 0. And so its height would be x squared minus 0. Again, you don't have to write the minus zeros if you don't want to. Now I can determine the bounds. I want to know how far left and how far right can these washers exist. Now if I take a look at the picture over here, I can see that very clearly the furthest to the left I can go is 0. But the furthest to the right I can go is wherever these curves are going to intersect. So let me move this green piece here. But wherever these curves intersect then is going to become very important. So I might want to know, when does x equal x squared? Well, again, to solve something like this, keep in mind it's never a good idea to divide by a variable. Instead, I'd like to subtract to one side and attempt to factor. Notice here then, I can see that the 2 points of intersection that I get are x equals 0 and x equals 1. So my bounds then will be corresponding to exactly these values. I can push this washer all the way back towards 0, or I could pull it all the way out towards the value of 1. So I'm going to have 0 to 1. This right here is actually a very, very simple integral to work with. You'll notice that it's actually just going to be pi x squared minus pi x to the 4th dx. This is so simple to integrate. Again, I'm not going to do it here, but I'll leave it for you to do, and hopefully you can confirm that this indeed turns into a 2 pi over 15. Now, this illustrates the idea that we will not always end up with circular cross sections. Sometimes we'll end up with these cross sections that have this hole in the middle, or these washers. And so we can summarize this down below in what we refer to as the washer method. Now, there's a lot of added detail here that's not really necessary. But what we can notice is, again, if I have a horizontal axis of rotation, that is, my washers stack up left to right, then I know I'm going to have a dx problem. And I know that I shouldn't be using just pi r squared, because that would give me area of a circle. I need to use area of big circle minus area of small circle to get the area for that washer. Then I can go ahead and use my bounds for wherever these values start and stop. However, I should be aware that if I was, again, just to rotate the picture of like what I had up here, imagine just kind of rotating this thing 90 degrees this way, I could have easily come up with washers that stacked in a vertical direction. And if washers stack in a vertical direction, I'm going to tackle this as a dy question, and then I can easily go ahead and imagine that I would still set up washers. I'm just going to have these in terms of y variables as opposed to in terms of x variables for the radii. In the next video, we'll take a look at 2 more examples of how we can actually do this with actually the exact same curves.